Hello everybody. So, I'm going to focus on some soil mineralogy and chemistry today. I'm going to go probably a little bit heavy on the mineralogy, but let's see how we do. So, in terms of where do we start? Let's start down with minerals. So, a mineral is a naturally occurring inorganic element or compound in which the atoms occur in a definite order. And we're going to talk about that order and why that's important. And then why are we talking about this in Introduction to Soils? And that's easy. It's just the fact that all soils are composed mainly of minerals. So when we're talking about minerals, what is it we're talking about? Well, here's some examples of some minerals. There's olivine, feldspar, halite, gypsum, hematite, calcite, quartz, muscovite, all pyroxene, all sorts of stuff in there. Different minerals, they all, you can see when you just look at these pictures, they look different. They offer different things. The colors aren't the same. The crystallizing, the shapes, the way that if you think about, like, if you broke them up into pieces, how the pieces would come off. There's all sorts of differences in terms of these minerals. And so then let's go from minerals to elements. And so when we're talking about the idea of elements and the things that are going to make up these minerals, so there's 8 elements that account for 98% of the Earth's crust by weight and 100% of the volume. Now that's impressive in itself that there's just 8 elements, but actually it's really just oxygen and silicon. Oxygen and silicon fit together to make up 95% of that volume and around 75% of that weight. And what's really important to understand is that the silicon-oxygen bond is very strong. And what they do is they form these silica tetrahedrons. And the silica tetrahedra, the plural of tetrahedron, so the silica tetrahedra, that make up what we're going to be talking about in terms of our soil building blocks, is just a combination of silica tetrahedrons. So the tetrahedron itself is one silicon ion surrounded by 4 oxygen ions. And then the silica tetrahedra will link up in various patterns and bond with metal ions to form specific silicate minerals. So, primary minerals that we're going to focus on form when molten rock cools and solidify, and most primary minerals are going to be silicate minerals. So they're going to contain mostly silicon and oxygen, which makes sense then if before we said the idea that the Earth's crust is mostly just silicon and oxygen. It's because if the Earth's crust is made out of all these minerals, and those minerals are mostly just silicon and oxygen, well, then that just makes sense. So let's take a look at that idea that we talked about. The shape and the arrangement of the silica tetrahedron will make a difference. So if we look here, we've got isolated tetrahedra or single tetrahedra, a single tetrahedron. So olivine would fall into that category. We have rings of tetrahedra, and you have like cordierite would fall in there. You can have single chains like pyroxene. You can have double chains, amphibiable. You can have sheets, which are going to be clay. Clay falls into the sheets category, so you get things like kaolinite and mica, which is from muscovite, that we'll talk about when we get into clay. And then you can have frameworks as well. So your feldspars, your quartz, those ones fall into framework. And you can kind of see the basic tetrahedron shape with that silicon ion in the middle surrounded by the oxygen ions. And then you can just take that tetrahedron shape and just link it up in all sorts of different ways. And those linkages, if we look over here on the right, it's how we form things like quartz, which we said is that framework tetrahedra. We got feldspar, over here, which is also the framework tetrahedra, and mica is in that sheet tetrahedra. So we're going to now focus on rocks because we started off with minerals. The minerals we know come from elements, and we know then that the minerals now make up the rocks. So let's talk about our three kinds of rocks, which we've talked about before: the igneous, sedimentary, and metamorphic rock. But if you need a good refresher on rocks and the differences between the rocks, I would hit pause on the video right now and click on the link in your lecture notes. So, just kind of going over and reviewing igneous rocks. Igneous rocks are formed when molten rocks cooled and crystallized. They are mainly composed of about a dozen or so minerals specifically. And you've got two types of igneous rocks. You've got extrusive and intrusive. So extrusive or volcanic igneous rock, that's formed from lava, because lava is when magma is spewed out. Usually that's going to be smaller igneous rocks, and then you also have plutonic igneous rocks, which are formed from magma under the Earth's surface, and you usually get larger rocks for that. And granite, which we are familiar with so far in this class because of the Sierra Nevadas and the fact that granite is such a huge part of the shaping of the Sierra Nevadas. Granite is a plutonic igneous rock. And so if you want to take a look at some igneous rocks, press pause again and click on the link. And so this example that I have right here in the picture, this is Devil's Tower, Wyoming, and that's a giant piece of igneous rock with a columnar look to it sticking out of the ground and just pushed up. Well, there's a few theories. One that, everything was up above there and it just kind of everything eroded away or receded, and that was the piece that stayed, or that was pushed up, or that was once the volcano part that would spew out was right above that. There's a few different thoughts as to why Devil's Tower looks that way, but for us, it's pretty cool to look at, and it's igneous rock, and it's a pretty sweet thing to go see. So one of the things that we cover in terms of the igneous rock and trying to tie it back into the idea of minerals is the idea of Bowens reaction series. So we have your book shows you just a chart of the names of these minerals, and just says, here these ones are at the top. But what I like about this picture that we got here is to actually kind of see it more in a different way, where we can see how it goes from an increase of silica to a decrease in silica, and things that are darker or less dark and have a less specific gravity to things that are going to be more dark and have a higher specific gravity. And what we can see here, if we combine this with some of the other things that the book talks about, is that the ones that are going to be the least stable in the soil, so the ones that are going to be easily moved out of the soil, so first to weather. So we've talked about weathering being the idea that with wind and water, you'll just get these things to move out of the soil. And so the first ones to weather are the ones that are going to be the least stable in the soil, and that's on the right. So those are also the reason they're the first ones to weather, is because they're the first ones to cool and crystallize. So as these things form over thousands of years, these ones like olivine and pyroxene and periodite, these ones are going to be the first ones to weather. They're the least stable in the soil. They're going to be the ones that are going to be the first ones to go. The ones like quartz and granite over here are going to be the last ones to weather. So we see these in a lot of our soils because they don't weather. They hold and they sit back. So we see those quite a bit more. They are much more resistant to weathering, and so that means that they're found in many soils or also in sedimentary rock, because they kind of, even though they got moved from one place to another, they sit there for a while. And so just using our local area, because we have our local area, might as well talk about it. It's Yosemite National Park basically is just this... when you look at the parent material, it is just this perfect patch of granite, and it's almost, what I was reading about it, the park's boundary is almost right where that parent material on this map lies, is basically your granite parent material is the whole part that makes up the park. And so you can see there's older metamorphic rock, and there's also some younger volcanic rock, and there's some alluvium as well, but the area where we get all the stuff that we find interesting is right there in the national park. On the right here is a piece of granite from Half Dome, the granodiorite, and you can see the dominant minerals within the granodiorite. So really trying to actually look at a piece of rock and actually see what makes up that piece of rock in terms of these minerals. So you can see it says at the bottom there, feldspar is either going to be white or pink. It's going to be okay. It's going to be opaque, and it's going to be rectangular prism shaped. You've got quartz, which is a gray-white color. It's going to have a glassy look. Going to be amorphous. You got biotite, which is going to be a black or dark brown color, and it's going to be book shaped. And then you got hornblende in there as well, which is going to be black or gray and blade shaped. And so you can pause this video again. You can check out the video about the formation of Half Dome, as well as about the climbing of Half Dome, and then the geology of Yosemite Valley. So, different granites will have unique chemical compositions that produce different mineral proportions. So these are going to be classified by their mineral proportions and given names such as granite or granodiorite or tonalite and dorite or diorite. And so this specific piece of granite right here, that's El Capitan. And we're looking specifically at the southeast face, which is this side right here of El Capitan. And so we can see, just like we did in the small piece of rock, we can see these different minerals at work. So we can see the hornblende rich diorite of North America. So that's these dark parts right here. That's that diorite coming in, and you got the lighter colored quartz, and then you got the feldspar rich parts of the El Capitan and Taft granites on this side. So remember we said that pinkish color, or and then with the quartz the whiter color, and then the dark color for the hornblende. Sedimentary rocks. So we've got our second category, sedimentary rocks, formed from the materials that settled in bodies of water and became cemented together, basically shoved together. The video, the rock video from a couple slides ago, really, I think, to me, did a great job with the starburst example of how sedimentary rocks will form together. And you can see here that we've got gypsum, and we got shale, and we got sandstone, but it's all piled on together, and that's how we can start figuring out how this one's probably a sedimentary rock formation. And so throughout geologic time, land masses were uplifted, and then they were eroded down to the base level. So basically, you got things pushing up, and then they get eroded away, and then all of that consolidates somewhere else. It gets carried away in streams, usually, gets deposited, and then sinks to the bottom and consolidates into rock. And so I've got another video about that process if you just press pause and take a look. So going back to Devil's Tower, because it's a great example, because we got two things going on. Here's Devil's Tower in the background, which is our igneous rock that pushed up from under the Earth's surface, or everything else eroded away. Either way, it works out. And then out here is actually sedimentary rock, and we can kind of see the different layers that form together. And basically all of this was covered by glacier and by water, and eventually that recedes away, and we can see we're left with some sedimentary rock on the outside, some igneous rock on Devil's Tower, and we start saying, why do we have these beautiful places, or why does the United States have some of these just unbelievably beautiful looking places? And it's because a lot of what has happened over millions of years of erosion and just geologic time, where these things have just been allowed to develop, and we can really look at it and appreciate it if we understand what's going on. Three kinds of sedimentary rocks. So there's clastic, chemical, and organic. So clastic is formed from the broken pieces of other rocks. So conglomerate, sandstone, siltstone, and shale are good examples of clastic sedimentary rock. You got chemical sedimentary rock, so formed by precipitation from seawater. You could also have it being water in lakes or water in oceans are going to basically evaporate, and then evaporites are going to precipitate, creating that sedimentary rock. And so you got halite, which is also known as rock salt, and gypsum being good examples of chemical sedimentary rock. And then you've got organic, so formed by the accumulation of plant or animal debris. So limestone was formed from skeletons of marine organisms. Coal, which we see here on the left, was formed from plant debris. So plant debris usually will accumulate in swamp environments, and that's why we find coal in swampy environments. And that's why coal is combustible and often used as fuel, because it's formed from plant materials. And then chert's another example. Chert is formed from the skeletons of smaller organisms like diatoms. And so if you want to pause and take a look at a bunch of different sedimentary rocks, there's a link right there. And then our third category is metamorphic rocks. So we got gneiss right there as an example. It's a foliated metamorphic rock. So we have two types of metamorphic rocks. So foliated, meaning it's got a layered or banded appearance, right? If we look at this, we can kind of see, it looks like there's a layer there and a layer there and a layer there. So it's got that layer or banded appearance. Or the other metamorphic category is non-foliated, so it doesn't have that layered look. And metamorphic rocks were formed when other rocks were transformed under heat and pressure. And so if you want to take a look at other metamorphic rocks, take a pause and take a look at the link right down there. And then that takes us to clay minerals. And so this picture right here, if I remember correctly, is an up close under an electron microscope of kaolinite. And so you can really see that idea of the sheets that we talked about, the idea of when we were looking at our structures. We talked about the idea of granular and blocky, and we can really see when you get this electron microscope and you get really down into it, the way that clay has that huge surface area, because it's just sheet after sheet piled on top of each other into these layers, and then it's layer upon layer upon layer, and that's why clay has such a huge surface area. So to be totally honest, I do not remember where I found this little infographic cartoon on the left-hand side, but I think it's great. It's a great little summary of clay. Clay is a product from the earth that when heated becomes hard, Geologically, clay comes from decomposed rock. It's typically carried by water and settles together in a particular area where it's mined. Chemically, clay is a combination of alumina, silica, and water, along with other minerals. Physically, clay's crystal structure is that of tiny sheets with water between them. The sheets are held together by suction, but can slide past each other like a deck of wet playing cards. The playing cards is always the easiest way for people to describe that clay structure. Heat causes the clay to harden. At 600 degrees Celsius, the water is driven off and leaves a bonded alumina silicate structure. Further heat, 800 degrees Celsius, causes melting of the free silica and other materials into a vitrified or glass-like substance. So, in terms of the structure of clays are composed of alternating layers of oxygen, silicon, aluminum, hydroxyl, and iron, if we want to go into all of it. But really, the focus is alumina and silica. And it's all held together by ionic bonds. Ionic bonds are relatively weak, positive, negative, attractive forces. The layers are going to be hexagonal or stop sign shaped, which if I go back real quick and we look at that, you can see that hexagonal stop sign shape going. The elements in and number of layers that you have and sheets, multiple sheets will make up a layer, but the elements in and the number of layers determines the type of clay and its properties. So just in going over what we've kind of talked about before, clay is our tiniest of particles. So if this is a particle of sand, that's what a particle of silt would look like. And then that little speck right there would be what a particle of clay looks like. And so, let me move myself out of the way. There's not really a good place for me to be, but I'll move myself over here just so you can hopefully clearly see what we have going on over there. So, in terms of silicate minerals, so you've got thousands of those silica tetrahedra linking together to form sheets in clay. And the sheets are going to stack upon each other to form layers, and then clays are going to have the different combinations of silica and aluminum sheets, and that combination is going to be notated like we see down here. So kaolinite, which is this one on the left here, which we saw in the previous slide, that has a 1-to-1 ratio, and what that means is the first number is silicon and the second number is aluminum. So in terms of sheets, kaolinite's made up of one sheet of silica and then one sheet of aluminum, and then that is stacked and stacked and stacked and stacked to form layers. In terms of mica, which is this one in the middle, you have a 2-to-1 ratio. So it's going to be a top silica layer, an aluminum layer in the middle, and then another silica layer. Merilionite, which is a type of smectite, is also 2-to-1, and you can have all sorts of different combinations of the silicon and aluminum sheets. You can have 0-to-1, 1-to-1, 2-to-1. There's all sorts of different combinations. But just to give you a look at kind of what that would look like down to the mineral structure, so you can look at the 1-to-1 like kaolinite. So what we would see down in here is that. So we've got our tetrahedral sheet of silica, and then our octahedral sheet of aluminum that is bound on. And if we had a 2-to-1 structure, so there's the silica tetrahedra on top, the aluminum octahedral sheet in the middle, and then another silica tetrahedral sheet on the bottom. So another thing to consider with clays is you've got oxide minerals. And so these are going to be important in old soils, and when we say old soils, we talk about the idea of highly weathered. So places where it's warm or humid or very well drained, areas where the things move through the soil quite a bit, and the soil's got to do a lot of work. Those areas you're going to see a lot of oxide minerals. Oxide minerals are also usually responsible for soil colors. You can see in this picture on the right all sorts of different colors, because we've talked about it in lab before, the idea that that really soil, without all this other stuff going on, would kind of have this grayish color to it, and instead we see all these different colors, and oxide minerals have a lot to do with that. Iron is going to be released by weathering, and it's free to form other minerals. So what does that mean? So you get ferric iron, is a specific type of mineral, combining with oxygen and hydroxyl ions, and those are going to form iron oxide minerals, and they're going to basically form what looks like a paint of coat on these soils. And if you look at this kind of specific example that I've shown you with all these colors, you kind of look at it and you go like, oh yeah, it's like it's painted on there. But what it actually is it's a bunch of small crystals. If you were to zoom in close enough, it's a bunch of small crystals on the top of the soil. There's 3 really common iron oxide minerals. That's goethite, hematite, and ferrihydrite, or ferrihydrite, whichever way pronunciation is more correct. There we go. Finally got it to change. All right. I guess I'll put myself back up here. Kind of still in the way, but that's okay. So Jackson's weathering index for clay-sized particles. So it goes from number 1, which are the most weatherable. So they're going to be abundant in soils of arid regions. Those are the ones that are most weatherable, and then 13 at the bottom, the rutile and zircon are going to be your least weatherable ones. And so number 2 there, calcite and apatite, we're going to see that in parent materials 3 through 6. So your olivine, pyroxene, amphibole, biotite, glauconite, albite, anorthite, obsidian, all of those are minerals that are going to be common in sand and silt. 7 through 10, so muscovite, cerussite, vermiculite, smectite, and kaolinite. Those are your clay minerals that are going to be common in temperate soil climates. So when you hear the word temperate, you're thinking warm. So you're not thinking cold, and you're not thinking hot. You're just thinking in the middle, warm. And then 10 through 12, so kaolinite, gibbsite, hematite, and goethite. So now we're talking about adding in those oxide minerals as well. Those are your clay minerals that you're going to see in tropical climates. And so then another thing that we cover when we talk about the chemistry of the soils is the idea of exchange capacity. And so when we talk about exchange capacity of a soil, it's the ability of the soil to hold nutrient ions, which are positively charged molecules, and release nutrient ions to plant roots. And so why does that matter, or what does that mean? And so if we look at this picture right here, we've got these clay particles in the soil. We've got the roots of our plants, and the roots of our plants have these root hairs on them. And you can see we've got the red stuff over here, and we've got some red and some brown and some blue over here, and it kind of all mixes together. And how does that work? And why does that work? And so one of the ways that it works is it's really going to depend on the internal structure of the clay, and then also the amount of organic matter that you have in your soil, because organic matter also really has a high exchange capacity. And the reason why exchange capacity is important is higher exchange capacity means more fertile soils, and exchangeable cation ions are a major source of plant nutrients. And so this is how we're going to get nutrients from the soil to the plant, and that's extremely important to us. And that's kind of one of the reasons why soil is so important, is because what it provides to the plants that we put in it. And so another kind of couple looks at exchange capacity. And so cation exchange capacity specifically when we're talking about cations, is the ability of the soil to hold and exchange positively charged nutrient ions with plant roots. And your important exchangeable cations are going to be potassium, magnesium, and calcium. Those three specifically are the ones that can be passed around in this exchange pretty easily. So looking at this clay example here in the top right, so this has a CEC, a cation exchange capacity of 25, whereas this sandy loam over here has a cation exchange capacity of 5. So one of them has more clay in it. So remember, more clay, more surface area, more positions to hold all these different cations that are being exchanged, whereas this one doesn't have that clay, has less surface area, so it's not going to be able to hold as many cations. If you have a heavier clay, you're going to go up to about 50 on the cation exchange capacity range, and if you have sand where you don't have any clay in it, you'll have a 0. So you have somewhere between 50 and 0 as your common range. So how does this work? So a clay particle, which is going to be negatively charged, is going to bind cations. So the clay particle itself is negatively charged, and all these cations are positively charged. And so because we're looking for balance, because it's negatively charged, it's perfect for these positively charged nutrient ions to bind on. So the cations then are going to get exchanged for hydrogen ions obtained from carbonic acid or from the plant itself. And then the mineral cations are going to get released into solution. And so you have to have balance. So if you're going to take something on, you got to give something up. Oops. There we go. So another look at it in kind of a more basic diagram. So you got the sheets of clay that we said that hexagonal stop sign shape, and I've got my sheets of clay. So in this example, we're going to take a fungicide spray, which is copper sulfate. So there's our copper and our sulfate. And so the copper cations are going to migrate towards the negatively charged clay. And if you say why, it's because one is negative and one is positive, so they're just going to attract each other. As the exchangeable ions vibrate within their outer sphere complex within the clay, those copper ions in the solution are going to be in constant motion. So then if we look at the right side of this diagram now, occasionally an exchangeable calcium ion vibrates to the outer edge of the clay's attractive charge field. At the same time, the copper one gyrates into the attractive field such that the copper becomes captured by the negative charge, and then the calcium one is then freed to diffuse away from the clay in the solution. So the two ions have exchanged places, and thus the idea of cation exchange. So the idea that this thing then took in a copper, but it gave up a calcium, and now the calcium can bind up with the sulfate, and then that's going to leach down through the soil. Another part of our soil chemistry that we went over in this chapter is the idea of pH. And so if you want a refresher about pH, pause the video right now and click on this little video on the right-hand side. And so when we talk about soil pH, we're talking about the level of acidity in the soils, and it's the way we're going to figure that out is basically it's measured by the amount of hydrogen ions in the soil. So if you have low pH, you're going to have higher acidity, which means you have an excess of hydrogen ions attached to the clay particles in your soil. And so this also is greatly going to influence the availability of essential nutrients, whether the nutrients are going to be available or not. One way, if you have an acidic soil, to deal with that is you can apply calcium carbonate or lime to your acidic soil to get it more towards this neutral pH. And 6.5 is about would be perfect for plant growth, but not everywhere is going to be at that 6.5 pH. So if we look at soil pH classification, so 0 through 6 are our acidic soils, 7 through 14 are our alkaline soils, 6.5, 7, that's our neutral soils, and then you can have, extremely acidic, slightly alkaline, very strongly alkaline. If we look at the pH scale, so right here in between 5 and 6, So we've got a desired range for mineral soils, and we got a desired range for organic and mineral organic soils. If you get way down here, your pH is too acidic for most crops. If you get way up here above H, your pH is going to be too basic or too alkaline for most crops. And so we actually end up with mostly acidic soils. We do have basic soils, and they're perfectly fine as long as it's not too much. And just like the acidic soils are fine because it's as long as they're not too acidic. And so why is soil pH so important? It's going to affect your health of plants. So before a nutrient can be used by the plants, it's got to be dissolved in water. It's got to be in solution. And so most plant nutrients dissolve when the soil is slightly acidic. That's why we want our soils to be a little more acidic, because most plant nutrients will dissolve when the soil's slightly acidic, but many plants are going to do well, really well between 6 and 7, and you can see some examples right there. When the soil is acidic, minerals such as iron and manganese are going to dissolve in soil water in small quantities. These plants will help these minerals will help plants grow, which is fantastic. But if it gets too acidic, these minerals are going to become too abundant. There's going to be too much of them, and then that can actually cause harm or kill the plants. And so you can see on the bottom right here, we've got soil pH and nutrient availability. And so if you look at our pH scale, you can see when we talk about the idea of our nutrients, where it's widest, that's where it's readily available, and where it thins out, it's not readily available. And so if we look at that kind of 5.5 to 7 range, we can see we hit a lot of what we're looking for in that 5.5 to 7 range. It gets real tricky above 8, gets real tricky below 5, but in that 5.5 to 7 range, we're pretty good on all of these essential nutrients that we really know that the plant needs. And so that's a real kind of quick basics on mineralogy and chemistry, but I really wanted to try and keep it simple for you guys, and really wanted to try and make it where it's not too overbearing. Make sure you read through your book, and if you have any questions, let's talk about it, and I hope you enjoyed it.